Alright, these are the solutions for Unit 2 practice exam. Question 1, Part A and B are from Section 3.1. And the objective here is you got to be able to write the standard form of the quadratic function. And from the standard form, you got to identify the vertex, range of the function, sketch the graph, all sorts of fun stuff. So what we're going to do in Part A is use the complete the square method. So what happens there in Part A, I'm going to move the 6 over. And then where the 6 used to be, that's where we need to add a value that completes the square. So what you do is you take your b value, in this case 4, you cut it in half, and then you square. So half of 4 is 2, 2 squared is 4. That's the number that completes the square. So I'm going to add a 4, and remember this is an equation, so what you do to one side, you got to do to the other. So now I've got f of x minus 2 equals this trinomial. Now that expression with 3 terms can factor into x minus 2 to the second power. And then you just move that 2 back over by adding. So you're going to finally have f of x equals x minus 2 squared plus 2. Now that it's in standard or vertex form, we know that this transformation moved the vertex 2 to the right, and this plus 2 moved the vertex 2 up. So the vertex is the point 2, 2. If we think about the graph, I'm actually do the graph first before I state the range, because it's easier to think of the range once you know the graph. So 2 to the right, and then up 2. And remember a parabola, I want you to graph at least 3 points. Vertex counts as one of those points. What I recommended is that you choose values on either side of the vertex. So we've got 1 and 3. So if I plug in a 3, for example, for x, 3 minus 2 is 1, 1 squared is 1, 1 plus 2 is 3. So 1, 3 is on the graph, and because of parabola symmetric, you know that 3, 1 is on the graph. So parabola looks like that, and we can see on the y-axis, looks like the lowest value right there comes right over to 2 on the y-axis, so the range is from 2 to infinity. Now for part B, it starts the same way. I'm going to move the 3 over. I'm also going to factor out that 2, leaving x squared plus 4x. And I'm going to close the parenthesis with enough space to add a value that completes the square. And again, you take the b value there, you cut it in half, and then you square it. So half of 4 is 2, 2 squared is 4. So I added 4 here, but you need to take into account the 2 that you factored out. 2 times 4 is 8, so I really added an 8 on the right side of the equation. So I've got to add an 8 to the left side to balance things out. So that becomes f of x plus 5. You keep the 2 factored out, this 2 right here, and then this factors into x plus 2 squared, and I got to move the 5 back over. So the expression becomes, or the equation of the function is 2 times x plus 2 squared minus 5. Now the vertex, if we use the transformations, this moves it 2 to the left, and that minus 5 there moves it down 5. So the vertex is negative 2, negative 5, and then if we wanted to graph two other points, I would choose values on either side, like on the other side of the vertex, like this negative 3 right here. If you plug in a negative 3 for that x, you're going to get negative 3 plus 2, which is negative 1. And then negative 1 squared is 1. 1 times this 2 right here is 2. And then 2 minus 5 is negative 3. So negative 3 comma negative 3. And because of symmetry, you also know that negative 1 comma, let's see, let's try that again. Negative 3 comma negative 3 would be about right there. There we go. And then negative 1 comma negative 3. This parabola is a little skinnier than the other one because we have this vertical stretch right there, that 2 in front. And in the range, if you look, the vertex goes down as far as negative 5. So the range is negative 5 to infinity. Okay. You've got to draw a picture of this one, I think, on question number 2. We want to build a rectangular enclosure, it says, so we've got a rectangular enclosure or rectangular pen, but it's subdivided into 2 equal parts, so there's going to be a subdivision inside the rectangular pen. So the dimensions need to be, what do the dimensions need to be to enclose the maximum amount of area? So if we want to label this with x's and y's, we can say, all right, there's x, this whole thing here from here to here, that's y. But then this one in the middle is also x. So if we want the area includes the space in between the whole thing. So that whole area is just the area of a rectangle, which is length times width, or in this case, x times y. See, now here's the problem. We've got 2 different variables, which is no good. So we need to come up with another equation. And they've given us the perimeter, 600 feet of perimeter. That's got to cover the entire outside of this, plus that little spot down the middle. And that's going to take the 600 feet of fencing. So we could say perimeter, which is 600 feet. I've got 2 y's, and I've got 3 x's. 2y plus 3x, that will include the entire 600 feet. So the trick now is to get one of these variables by itself and then plug that into this other equation so you can only have one variable. So what I'm going to do is try to get y by itself. So I'm going to move the 3x to the other side. And then divide everything by 2. So I know what y equals now. Y equals 300 minus 3/2 x. That also means that this y equals 300 minus 3/2 x. So the trick now is to take this expression and plug it in there for that y. So that area has a new formula now. Instead of area being x times y, area equals x times the substitution for y, which is 300 minus 3/2 x. If you distribute the x, you're going to have area equals 300x minus 3/2 x squared, or if you write this another way, negative 3/2 x squared plus 300x. Now I know this area formula looks more complicated than what we started with over here, but the nice thing is we only have one variable, x. So really what this boils down to is finding a maximum amount of area. Remember the word maximum or minimum when we're dealing with parabolas, all that really means is find the vertex. So coming back here, if you remember that the vertex formula is the opposite of b divided by 2a. So this is b right here, 300. The opposite of that is negative 300 divided by 2 times negative 3/2. That's the a value. The 2's there would just cancel. So it's negative 300 divided by negative 3, which is 100 feet. And remember the vertex solves for the x. The vertex formula rather solves for the x value of the vertex. We know that x equals 100. So that's 100, that's 100, and that's 100. That's 300 feet of the fencing right there. And if we only have 600 to begin with, then that leaves 300 feet to split between that y and that y. So 300 split evenly is 150. So we know that this has to equal 150, and that's got to equal 150. So the dimensions are 150 feet by 100 feet. So that answers the first part of the question, what would the dimensions have to be? The second part of this question is what is the maximum area? Well, now we just got to use the area formula, which is length times width. 100 times 150 is 150,000 feet squared. So here are the dimensions. Let's just make sure we have everything written down. So there's the dimensions, and this would be the max area. All right, question 3. Looks like we've got a little bit of a typo here. That should be to the second power, negative 16t squared. So luckily we've already been given a function. We don't have to come up with a function. And here's that key word again, maximum height. How many seconds does it take for the rock to reach the maximum height? And what is the maximum height? So again, really remember this just means find the vertex. So the vertex formula, as in the last problem, is the opposite of b over 2a. So our b value is there, that's 32. And the a value is negative 16, so it's 2 times negative 16. Rather, we need to do the opposite of b, so that would be negative 32. So we get negative 32 divided by negative 32, which is 1. And remember the vertex solves for the quote-unquote x value of the function. We don't have x's, we have t's. So this vertex is solving for the t value, so 1 is equal to t. So now you got to try to figure out what t represents. T represents time. So you've got to figure out the meaning of this expression t equals 1. Does that mean the ball goes 1 foot in the air, or does it take 1 second to reach its maximum height? Well, remember t is a value of time, so this is seconds. It takes 1 second to reach maximum height. And then the next part of the question, what is the maximum height? That's what h stands for. So the height at any given time is given by this formula. So we want to find the height at 1 second. So all you got to do is plug 1 in for all of the t values. We have negative 16 plus 32 plus 100. So that equals 116 feet. Alright, this is from section 3.3, objective 1, using long division. One thing students always like to forget when doing long division, and synthetic division for that matter, in this next question here, but you've got to look at what you're dividing and what you're dividing by. If there's any missing terms, like there's a missing term there should be an x term. And same thing here, there's a missing term in the middle, there should be an x term there. You've got to represent those missing terms with zeros. So I'm going to say 2x cubed minus 5x squared plus 0x plus 1 is going to be divided by x squared plus 0x minus 3. So we've got to think, how many times does x squared go into 2x cubed? And the answer is 2x times. Because when you multiply 2x by x squared, you get 2x cubed exactly, and that's what you want. You want those terms to match. So 2x multiplied into that expression is 2x cubed plus really 0x squared, and then minus 6x. Remember the phrase, draw the line, switch the sign, so change all of these. First terms cancel out. Negative 5x squared minus nothing x squared is still negative 5x squared. And 0x plus 6x is positive 6x. Drop down the 1, and then you got to think, is this the remainder or can you continue? You've got to compare that is a second degree term and that's a second degree term, since they're still the same degree. As long as this is the equal degree or higher, then you keep going. So how many times does x squared go into negative 5x squared? And the answer is negative 5. And then I multiply the negative 5 into that expression, and we get negative 5x squared plus 0x plus 15. Remember to draw the line, switch the signs. Leading terms cancel. 6x take away nothing is 6x, and then 1 minus 15 is negative 14. Now you compare first term and first term. Since this has a lower degree, now you're done. That's the remainder. So the way you represent your solution here is when p of x was divided by our term d of x, the solution was that expression there, that's the quotient, 2x minus 5, and then you add the remainder as a fraction. So we've got 6x minus 14 over your divisor, which is what you divided by, x squared minus 3. Now question 5, use synthetic division. This is still in section 3.3, objective 3, and well, 2 and 3. Objective 2 was, can you do synthetic division, and objective 3 is, can you evaluate a polynomial using synthetic division, using the remainder theorem. So let's do the first part, which is just dividing our polynomial by so p of x needs to be divided by d of x. So we're going to take this and divide it by that using synthetic division. So synthetic division algorithm, we're only looking at the coefficients. So there's a 1, a negative 7, a 17, and a negative 20 there. So 1, negative 7, 17, negative 20, and then you synthetically divide by the 0 of your divisor. So that would be positive 4. The 1 drops down. And then these on the outside multiply. These add. Those multiply. These add. And those multiply. And that's your remainder. Since it had no remainder, and this is pretty significant in this chapter and in this unit, if you have no remainder, that means that that's a 0. So x equals 4 is a 0. That also means that x minus 4 is a factor of that polynomial. That's pretty significant, something you're going to want to remember. So anyway, p of x divided by d of x, and you get the quotient from those coefficients. So that's going to be x squared minus 3x plus 5. And if there was a remainder, let's say that was another number besides 0, then you would add whatever number that is over your divisor, x minus 4, but because we had no remainder, we don't need to add the remainder because it wasn't anything. So that's That's p of x divided by d of x. Now the second part is to evaluate p of x at x equals c. All that really means is, and this is not something else you're going to want to remember, evaluate just means find p of 4. Just find p of 4. What they're not wanting you to do is just plug 4 in for all the x's. Remember, there's another way to evaluate a polynomial. We learned this in section 3.3. It's called the Remainder Theorem. If you're going to evaluate a number or evaluate a polynomial at a specific number, then all you do is the synthetic division at that number, and whatever the remainder turns out to be is what the value of the polynomial is at that point 4. So p of 4 equals 0. That's what you would get if you plugged 4 in for all of these x's and evaluated the polynomial. P of 4 equals 0. What that means, again, I said this before, that it means that 4 is a 0 of the polynomial. It also means that x minus 4 is a factor of the polynomial. Or x equals 4 is an x-intercept of the graph of this polynomial. All right. Question 6. We got to make a list of possible rational zeros using the past rational zeros theorem. Factor the polynomial once we find zeros, and then sketch the graph. So, possible rational zeros. Remember, you got to take the factors of that number and divide it by the factors of the leading coefficient. And since the leading coefficient is just 1, any factor of this divided by 1 is just whatever number that was. So I'm just going to take the factors of 6, which are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are the possible rational zeros. Now what you got to do is, from this list, you got to just test them until you find one that works. Something to keep in mind that students, again, love to forget is there's a missing term here. There should be an x squared term. So you got to represent that when you're doing synthetic division. So I'm just going to start with the number 1, see if it works. Taking these coefficients, again, remembering there should be a 0 where the x squared term should be, and let's see if this works. Right out of the get-go, we find one that works, it looks like. That's fantastic. So what this means that x equals 1 is a 0. But more importantly, to answer part B, factor the polynomial, we need to find factors. So if x equals 1, then x minus 1 is a factor, and then those are the coefficients of a quadratic factor, x squared plus x minus 6. And luckily, our quadratic factor can break down even further into, so we've got the x minus 1 that we started with, and then x squared plus x minus 6 is x plus 3 and x minus 2. So the zeros, or the x-intercepts, are x equals 1, x equals negative 3, and x equals 2. So wanted to put those on a graph. And all of those have multiplicity 1, which means the graph's going to cross through at each of those x-intercepts. Now remember, when we graph, I also want you to find the y-intercept. You find the y-intercept by letting x equal 0. So if all the x's are 0, that x is 0, that x is 0, that leaves us with a positive 6. So the y-intercept is positive 6. And we started with the third degree polynomial, which means it has end behavior where one side's going down, one side's going up. And since we have a positive leading coefficient, that means the right side's going up to positive infinity, and the left side's going down to negative infinity. So we just need, these two sides to connect somehow. So we know that this left side here, when it reaches this x-intercept, it crosses through it because it has odd multiplicity. Now we need to find out if it goes right to that y-intercept, or it may go actually a little bit higher and then come back down through it like that. So we need to plug in, let's say we plug in negative 1 to see where that takes us. So if we plug in a negative 1 for all the x's, negative 1 cubed is negative 1, Negative 7 times negative 1 is positive 7. And then you add 6. So that's all the way up at 12. So negative 1 is way up here at 12 somewhere. So it looks like it goes up a little higher, then comes back down through the Y-intercept, then it comes down to that 0, crosses through, and we know at some point it's going to have to turn back up because it's got to reach that other 0 or that other x-intercept. Now there's not a real good number to plug in between x equals 1 and x equals 2. You'd have to plug in a decimal. I don't expect you to do that. So just at some point make sure it turns up, connects with that other side right there. Now part B starts the same way. We need a list of possible rational zeros. So possible rational zeros. We need the factors of 8 divided by the factors of the leading coefficient. And again, the leading coefficient here is 1. So if you divide any of those factors by 1, that's not going to change the value of those. So I'm just going to take the factors of 8. So that's plus or minus 1, 2, 4, and 8. Now I got pretty lucky with 1 last time, so I'm going to try that one again. So 1, it looks like this one has no missing terms, so I don't need a 0 in there. So 1, 4, negative 3, 10, and positive 8. Let's see what we get. Wow. Wow. So x equals 1 turned out to work. I like that. So that means x minus 1 is a factor. But we got to think carefully now. Those are coefficients of a third degree polynomial now. So it's x to the third plus 5x squared plus 2x minus 8. So since this is not a quadratic, I can't go right into factoring or into the quadratic formula. I need to go back to my list of possible rational zeros and keep testing. See if I find another one that works, but I'm going to test it now on this reduced polynomial using synthetic division. So I guess we could try negative 1. Now I'm going to use these coefficients from that reduced polynomial. So that's 1, 5, 2, negative 8. Okay, so that didn't work. Negative 1 didn't work. We could try 2. Okay, that didn't work. We try negative 2. There we go. So negative 2 worked. So now I know two factors. I knew that x minus 1 was a factor because of that. And now I know that x plus 2 is a factor because of that. So I've got x minus 1 for my first go around, and now I know that x plus 2. And then these tell me the coefficients of x squared plus 3x minus 4. And now I got to look at this quadratic and think, all right, can that factor, or do I need to use a quadratic formula? Looks like that'll factor. So I've got my x minus 1, I've got my x plus 2, and then x squared plus 3x minus 4 is x plus 4 and x minus 1. So looks like we have a repeated factor of x minus 1 squared. So I'm going to run out of room there. So it's x minus 1 squared, x plus 2, and x plus 4. So my zeros are x equals 1, but that's got a multiplicity of 2, which means the 0 bounces there. Then I've got x equals -2, and I've got x equals -4. So if I want to graph those, those would be my x-intercepts. And then I need my y-intercept. So if I go back to the original function and let all of these x's equal 0, I'd be left with +8. So 0, 8 is my y-intercept. And I started with a 4th degree polynomial, and the leading coefficient is positive, which means the left side's going up to positive infinity and the right side's going up to positive infinity. So if I try to connect the left side, I get to this first 0 of -4, my first x-intercept is -4. I check the multiplicity is odd, which means it crosses through. And then it's eventually got to turn up and come back up to that x-intercept there. So I need to find out a little bit more about where that exactly turns up. So I got to plug in that -3, figure out how far down that graph goes. So if I plug in a -3 and raise it to the 4th power, that's 81. -3 cubed is -27. -27 times 4, oh boy, let's see. That's got to be -108. And then -3 cubed is 9. 9 times negative, that's -27. And then that's a +30. And then I got a +8. Gonna need a calculator for this one. So let's see. Let's see. I check my math there. All right. So I got 81 minus 108 minus 27 plus 30 plus 8. So that's -16. Goes all the way down to -16. So that's way down here at -3, -16. So it comes way down there, and then it comes up here. And it crosses, well, let's check. At -2, it crosses through, and it might go right to there, or it might come up a little bit higher and come down. We got to be sure to check what happens there at -1. So if I plug in a -1 for all the x's, actually, instead of going to the original, it might be easier here to use the factored form. That might be a little more manageable. If I plug in -1 there, I get -2. If I plug in -1, I get 1. If I plug in -1, I get 3. If I plug in -1, I get -2. So -2 times -2 is 4. 4 times 3. So it goes up to 12, it looks like. So -1, -12, way up there. Then it comes down. Now we're at that 0, and that has a multiplicity that's even, so it's got to bounce off of that one, come up there. Okay, hopefully you got my message that there was a typo when I originally sent this out on question 7. It's supposed to be degree 3, but there was one too many zeros. So I took off one of the zeros. I think it used to be 1. So right now the zeros are x equals -2 and x equals 1 minus 3i. So if you remember in class we talked about these kind of zeros. Those are complex, non-real zeros. they always come in pairs. So the one that they didn't give us in the problem has got to be 1 plus 3i. So those are my three zeros. What I now need to do is put these zeros into factors. If x equals -2, that means x plus 2 is one of my factors. With these complex zeros, remember I suggested that you move all of these terms over to the other side to be with the x. So that was going to be an x minus 1, and then I'd have to add the 3i. So it would be x minus 1 plus 3i. And then here, if I subtracted the 1 and then subtracted the 3i, that would give me x minus 1 minus 3i. So there's my polynomial in the form of its factors, but what it wants is a polynomial in the form p of x equals x to the third plus blah blah blah. So we need to multiply all these factors together. I'd recommend that you do these two first using the FOIL method. So that times that, and then that times that, then that times that is negative 3i x. Now do the -1 term here in the, so -1 times x is negative x. -1 times -1 is plus 1, and -1 times -1 times negative 3i. Let's see. I think I just erased something here. Hold on. X times x squared, negative x, and then negative x plus 1. That should be a 1. And then plus 3i, there we go. Now we multiply the 3i to the x, that's positive 3i x. 3i to the -1 is negative 3i. And then 3i times negative 3i is negative 9i squared. Now the 3ix and the negative 3ix cancel. The 3i and the negative 3i cancel. And remember, I squared is -1. So it's really negative 9 times -1, which is a plus 9. And that plus 9 is going to combine with that plus 1. And then the negative x and the negative x combine. So that turns out to be x squared minus 2x plus 9. And then we have this x plus 2. So if we multiply that together, we're going to get x cubed minus 2x squared plus 9x plus 2x squared minus 4x plus 18. Combining like terms, we get x to the third. Looks like our x squared terms are going to cancel, so we got a plus 5x, and then plus 18. Alright, I don't know, I might have overdone it on this one. I gave you a few problems to do. So we're going to split the paper up here. Let's do part A over here in this corner. So we need a list of possible rational zeros. That's going to be plus or minus 1, plus or minus 2. So I'm going to start testing them. Alright, cool. Found one that works. So I know that the polynomial is x minus 1 and then x squared minus 2x plus 2. Now this does not factor, so we have to use the quadratic formula. So the value underneath the square root is 4 minus 8, so that's negative 4 The square root of negative 4 is 2i. And then 2 plus minus 2i all over 2 is 1 plus or minus I. So what do they want us to do? Find all the zeros. So for this one, the zeros were x equals 1 and x equals 1 plus or minus I. Part B starts the same way. We need a list of possible rational zeros. So I'm going to say, well, 13 is kind of nice because we don't have many choices. It's a prime number, so plus or minus 1, plus or minus 13. I'm going to go out on a limb here and say that 1's going to work. Hopefully it does. Let's see. Looks like it didn't. So try negative 1. There we go. So that proves that negative 1's a 0, which shows me that x plus 1 is a factor. And those are the coefficients of a quadratic term, x squared plus 4x plus 13. This does not factor, so again, quadratic formula. So let's see, negative 4 plus or minus the square root. We're going to get 16 minus 4 times 13. Let's see, that's 52. So let's do 16 minus 52. That's negative 36. The square root of negative 36 is plus or minus 6i. And then that's negative 2 plus or minus 3i. So the zeros were x equals negative 1 and x equals 2 plus or minus 3i. So for part C, boy, we got a few more possible rational zeros there on part C because we've got 40 divided by 1. That could be a lot of them. All right, we got plus 1, 2, 4, 5, 8, 10, 20, and 40. It's a huge list of possible zeros. So let's see what we can come up with here. So what are my coefficients? I need a 1, negative 6, 14, negative 24, and 40. All right. Not looking good. This doesn't look like 1's going to work. Try -1. Okay, not looking good there either. Let's try 2. Nope. Boy, I hope we find 1 soon. Nope. Let's do part D there, our possible rational zeros are 1, 2, let's see, 4, 26, actually 13, 26, and 52. So let's try +1. Okay, that one didn't work. Maybe -1. This better not turn out like the last one. Oh, there we go. We got one. So I know that x plus 1 is a factor, and these coefficients tell me the other factor is going to be x cubed minus 4x squared plus 30x minus 52. So since we don't have a quadratic yet, I need to go back to my list here and test a few more numbers on this polynomial. So let's see, let's do 2. See if it works on the smaller polynomial. All right. All right. Let's see. So x plus 1 came from that 0. And then from this one, I'm going to get x minus 2. And then from these coefficients there, I'm going to have x squared minus 2x plus 26. Now, that's going to have to be a quadratic formula. X equals the opposite of b, plus or minus. So there's our quadratic formula. So we've got inside the square root, we're going to have 4 minus 4 times 26. That's 104. So 4 minus 104 is negative 100. The square root of negative 100 is 10i. So this is 2 plus or minus 10i all over 2, which is 1 plus or minus 5i. So zeros were x equals negative 1, x equals positive 2, and x equals 1 plus or minus 5i. So I think we had all of our zeros listed. Again, I took out part C because it actually didn't turn out to have any real zeros, no rational zeros, no real zeros. They were all imaginary. Makes them pretty difficult to find, so let's not worry about it. Okay, this question 9 is from section 3.6, objective 3, which was I can graph a rational function. What that includes is being able to find the asymptotes and the intercepts. So for part A, I'm going to start with the horizontal asymptote, and we need to compare the degree of the polynomials being divided. We've got a large degree in the denominator. What that means is the horizontal asymptote, if you remember, is y equals 0. Vertical asymptotes, if we look at the denominator in factored form, we're going to have x plus 2 and x minus 1, which means we're going to have a horizontal asymptote, or vertical asymptote rather, that x equals negative 2 and x equals positive 1. Now the intercepts, let's do the y-intercept. If you remember, you let all the x's equal 0, so if you come over here and let all of these x's equal 0, we're going to have negative 2 divided by negative 2, which is positive 1. Now the x-intercept you find by letting y equal 0. And remember, in this case, f of x is y, so y equals 0 or f of x equals 0. And a fraction like this only equals 0. We talked about this in class when the numerator equals 0. So what makes x plus 2 or x minus 2 equal to 0? That would be positive 2. So the x-intercept is positive 2. You have the information you now need to graph. The horizontal asymptote is right there on the x-axis. Got a vertical asymptote here at negative 2. And another one at positive 1. We got a y-intercept at positive 1 and an x-intercept of positive 2. Okay, so now we got to figure out how this graph all pieces together. So I'm going to start on the left side over here. I've got two options. Either the graph is kind of up there in that corner, or the graph is down here in that bottom corner. So what I need to do is plug in a test value. So if that's, let's say, okay, that's negative 3. I'm going to plug in negative 3 into the function, see what happens. So if I go back here, plug in negative 3 up top, that gives me negative 5. And I'm going to have negative 1 times negative 4. So I'm going to have negative 5/4. So negative 3 gave me negative 5/4, which is, so negative 3 comma negative 5/4, right about here. What that tells me, if one point is underneath the horizontal asymptote there, and there aren't any x-intercepts anywhere in this vicinity, then all of the points are underneath. Now here in the middle, got to figure out what's going on. I'm just curious, where are we when x equals -1? I'm just going to test a point right there. So go back up here, -1 minus 2, that's -3. -1 inside of there gives me -1 plus 2 is 1. And then -1 minus 1 is -2. So -3 divided by -2, that's 3/2. That's 1.5. So -1 comma 1.5. That's right about there. So I know the graph looks like that, and then it's got to cross through the y-axis, and I can either go up to positive infinity or I can come down to negative infinity, but I can't come down and cross the x-axis right there. There's no x-intercept, so I know the graph has to go up to positive infinity right there. Now I'm a little concerned right here on the right side because we got this x-intercept, which is in kind of a weird spot. If you're ever unsure on a graph, the safest thing to do is just plot points and start graphing away. So with that, I'm going to test x equals 3. I'm going to test x equals 4. I'm also going to, even though it's a little bit more difficult, I'm going to test in between there, between 1 and 3. Or sorry, between 1 and 2, that's 1.5. I'm also going to test 1.5, just to give me an idea of where things are. So I'm going to start with x equals 3. If I plug in a 3 for all my x's, 3 minus 2 is 1, 3 plus 2 is 5, 3 minus 1 is 2, so that's 1/10. So 1/10 is just barely above. So now if I plug in 4 minus 2 is 2, 4 plus 2 is 6, 4 minus 1 is 3, so that's 2/18. So that's 1/9. It's still pretty tiny. Now for 1.5, minus 2 is negative 0.5. 1.5 plus 2 is 3.5. And 1.5 minus 1 is 0.5. Now, I'm not so much concerned about what that number turns out to be. What I'm concerned about is it's negative on top and it's positive on the bottom. What that tells me is that comes out to be a negative number. So at 1.5, I've got some negative number right here. So if I connect all these points, what this is telling me is I'm coming down to negative infinity. I do actually cross through the x-axis, but remember, the graph's not just going to come up like this and go on forever, because that's what this horizontal asymptote is here to describe. It means eventually when x heads towards positive infinity, the graph needs to head towards that asymptote. So what ends up happening here is it does cross through, and then it just comes down and gets closer and closer to the horizontal asymptote y equals 0. All right, for part B, we look at some of the factored forms. It's going to be x and x minus 3 in the denominator. Let's see if we can factor the numerator. So I'll need a 2x and an x, and I'm going to have a, let's see, like a minus 3 here, and a plus 1 there. Will that do it? Yeah, that'll do it. All right, so let's start with the horizontal asymptote here. If we compare the degrees, they're the same degree, which means what we need to do is divide the leading coefficients. 2 divided by 1 is 2, so we get the line y equals 2. Vertical asymptotes are going to come from domain restrictions. X can't be 0, x can't be 3, so we have a vertical asymptote at 0 and a vertical asymptote at 3. So the y-intercept, if we let all the x's equal 0, actually isn't going to work, because if we let all of those x's equal 0, we're going to have a 0 in the denominator. So there is actually no y-intercept, which makes sense now that I think about it. If we've got a vertical asymptote there at x equals 0, that is the y-axis, so we're not going to have any point there. So no y-intercept. I should have saw that one coming. X-intercept we can find by letting the y equal 0, which is just f of x equals 0, and a fraction only equals 0 when the numerator equals 0. So the numerator is going to equal 0 when x equals -1, and also when x equals 3/2, because we have these two factors right here. Gives us 2 zeros. Alright, we have what we need. Got a horizontal asymptote up here at 2. Vertical asymptote at 0, that's right through the y-axis, and +3. And x-intercepts at -1 and 3/2, or 1.5, which is right there. Alright, I'm going to start on the left here. Now I already know that I've got a point right here that's underneath, that point is underneath the horizontal asymptote. So that already tells me that this piece of the graph is going to look like that. I'm going to skip the middle part here for a second and go right over here to the right side. I've got one of two options. Either it's up here in the top corner or it's down here in the bottom corner, but I know it's not going to be down here, because if it is, I'd have to have an x-intercept somewhere over here to allow it to cross through the x-axis, which I don't have. So I know that that piece of the graph is up there. So I'm just going to decide what's happening here. Does it kind of look like that? Does it look like that? Or it could, you know, be one of these things that bounces, or I suppose it could be one of those where it bounces like that. So we just, again, safest thing is to test points. That's where x equals 1. That's where x equals 2. Plug them in, see what happens. So in the numerator, if x equals 1, we're going to have 2 minus 3, that's -1, and 1 plus 1, that's 2. So I get a -2 in the numerator. And then 1 times 1 minus 3, that's -2. 1 times, that's -2. So it looks like we're going to have a +1 there. So 1, now when x equals 2, 2 times 2, I'm looking right here, 2 times 2 is 4, 4 minus 3, so that's a 1, 2 plus 1 is 3, so I get a 3 in the numerator. And then 2 times 2 minus 3, that's -1, so I get a -2, that's -3/2, that's a negative number. So that tells me, you know, it's down here somewhere in the negative realm. So it looks like we have one of those deals. Alright, question 10, graphing a polynomial that's already been factored. So this is actually pretty easy. This is from section 3.2, objective 2. So for part A, we had to at least state what the zeros are. The zeros are x equals 0, that comes from that factor right there. X equals 2, that comes from this factor right here, but that's got multiplicity 2, and then from that factor we get x equals negative 2. So this is a fourth degree polynomial. So we would also want to figure out the y-intercept. Remember, that's when you let all the x's equal 0, so 0, and then we've got a 0 for that x. 0, this first 0 times the whole rest of this thing is just going to be 0, so we've got a y-intercept at 0. Right there, and then we had positive 2, and we also had negative 2. Since it's a fourth degree polynomial, the end behavior, right side's going up, left side's going up. So go starting here at the left side, it's got to cross through negative 2. And then we better find out what's happening there at negative 1. So we've got negative 1, and then negative 1 minus 2 is negative 3 squared, that's 9. And then negative 1 plus 2 is 1. So that looks like it goes all the way down to negative 1, negative 9. And then it comes up here, crosses through that one, and then looks like we got to figure out what's going on a positive 1. So that's a positive 1 there. 1 minus 2 is negative 1, squared is 1, 1 plus 2 is 3. 1 times 3 is 3, so it goes up to 3. Comes down there, bounces off that one because the multiplicity was even. And for part B, we've got zeros at x equals 1 and x equals negative 2, but that one has multiplicity 2. Alright, the y-intercept, if you let all the x's equal 0, for part B, we're going to have 0 minus 1. That's negative 1. 0 plus 2. 2 squared is 4. 1 times negative 4 is negative 4. And this is going to be a third degree polynomial because it only has 3 factors. So third degree, we've got a 0 here at x equals 1, and negative 2 and a y-intercept down here at negative 4. A third degree polynomial that has a positive coefficient means that the left side is going down and the right side going up. So when it gets to negative 2 here, remember it bounces because it has multiplicity that's even there. It bounces and then it's got to come down. Maybe it goes down a little bit more and comes back. So we got to find out what's happening there at negative 1. So negative 1 minus 1, that's negative 2. Negative 1 plus 2 is 1. 1 squared, 1. So it looks like it's just negative 2. So looks like it just kind of heads right down there. Goes right up through there. Connects onto that.